So we present to you Crypt4GH in the real world. So we have presented Crypt4GH before, but right now we're connected to some application in the real world. But we also have 1 hour, so we can explain a lot more about Crypt4GH without going into the cryptographic details. So we want to explain why secure sharing of genomic data is vital for collaboration, and we will do that in 4 parts. First, we present the current landscape, so what are the challenges and why we need it. And we are going to present as well what Crypt4GH is. So what's the design? We introduce it, we show the benefit of Crypt4GH, and then we will run 2 demos. So the first one where we download some files and securely using Crypt4GH, and then the second one where we run some analysis. And then there will be some time for a conclusion. So this first part would be the why we do that. The second one would be the what we are doing. And the third one would be that how we connected it in the real world. And I'm going to keep these words. In this talk, we are going to talk about security in a way that we make the researcher access the data as if the security was not on the way and it was not cumbersome. And the reason we do that is that the genomic data is under access control. So there is a data access committee that grants permission to the different files to an approved researcher. And if the researcher is approved, they can access the data. And by law, the data must be encrypted. So in Europe, it's GDPR. In the US, it's IPA. And the data as well could be downloaded to different researchers or different tools. And the objective of this talk is this part over there about Crypt4GH. So the question is whether we can make it secured, performant, personalized, easily shared, integrated, and then you name it, you can add to the list. How do we actually do it? And this, I hope by the end of the talk, you will have a good idea about how we made it happen using Crypt4GH. So primer on security. So you have Alice. Alice has a file, and the file is private for Alice, and she would like to send the file to Bob without a hacker somewhere in the middle, very often called Oscar. And the hacker should not have access to the original file of Alice, or should not have access to the file while it is in transit. So not at rest, neither in transit. And it should not be able to trick Alice into sending the file by claiming being Bob. So these are classic problems in cryptography, in security. And there are plenty of cryptographic solutions for that. This is a classic problem of identification and data encryption. That said, Alice now has a file that is really big, and she puts it into a cloud. She doesn't really know what the engineers of that cloud are going to do with the file, and she doesn't know what happens when there is a data breach into the cloud. So to be sure, she just encrypts the file. And she could encrypt it with any tool she wants, but then when Bob downloads the file, it will have to decrypt the file, and then the download should re-encrypt the file for Bob. But this gets more complicated because then if you have multiple downloads, you have to re-encrypt for each of them. So can we actually avoid the entire re-encryption altogether? And we should always make sure that the hacker cannot download the file either. And then there is one more question, which is what happens if you actually just want to read one part of the file and not the whole file? So this is why we introduced some time ago, we introduced Crypt4GH, a globally standardized file format for keeping genomic data encrypted throughout its lifetime, from storage, analysis to transfer. So whether the file is on disk, whether the file is transferred, or the file is inside some analysis, the file should stay encrypted and never be visible on disk or in transit unencrypted. So I will first describe the file format, and then I will leave the storage, analysis, and transfer part for the demo. We'll see that during the demo. So what is Crypt4GH? You start from the original file. You encrypt the file using a symmetric algorithm, and then you end up with encrypted data. And the algorithm we have chosen is CHA-20 and the MAC is poly 1305. So this is the only thing I will mention in this presentation about the cryptographic choice we have made. But if you have used HTTPS or SSH with a rather modern web server, you are actually using CHA-20 poly 1305. So you end up anyway with encrypted data in chunks. And so we take the original file, we chunk it in pieces, and then we encrypt each of the pieces into a box. And in order to do that, we need to have a key. This CHA-20 is a symmetric algorithm. That means the same key is used for encrypting and for decrypting. And we should not lose that key. So what we do is we put it at the beginning of the file into a box itself, and then we lock the box using something that is private to the user. We call that part the header, and we call the second part the payload, or the segments, or the data portion. And the advantage of chunking the file is that the day we want to inspect only some part of the file, we don't have to decrypt the entire file. To do it, we can just decrypt one chunk, and then we will get access to the data. And you will see that a bit later in the demo. So this is Crypt4GH in a nutshell. Using this presentation. However, there is, of course, a formal presentation of it, and there is one part related, so here it is, and there is one part related to the header. So if you, it's like a protocol. If you align the byte according to this recipe, then you will have a Crypt4GH file that will be able to be parsed by another tool that understands Crypt4GH. So just to cut short, this is the place where the yellow key that we shouldn't lose is, and this is also where we describe the private part and the public part of the user. The second part is the data, the encrypted data that we have divided into blocks or segments or chunks. And then you see in the middle that you have some encrypted data somewhere in the middle. And you also see that there is a MAC, which means it stands for Message Authentication Code. So it's a built-in data integrity. It's like a checksum of the encrypted data. But on steroid, it's a better one. So only the person that has the yellow key can compute the correct MAC. And that way, if somebody changes even a single bit of the encrypted data, the MAC will actually detect it. So we are preventing somebody to change the file under our nose, and we will not even detect it. So this is Crypt4GH. And what we have done is if you encrypt the file with a new key, with a new yellow key all the time, then even if a hacker comes into your system and gets their hands on one file and manage to hack and decrypt one file, they will get their hands on the yellow key. That's great for them for that file, but then it will take forever to actually, this key is useless for the other files. So, and actually, cracking the key would take, I don't know, 115 years or something like this. It's faster to go fetch the person that has the DNA and resample it. So now, what are the benefits of Crypt4GH? The data remain encrypted in storage, transit, and in use. The private key enables the use of shared resources. You have efficient sharing without re-encryption. And this, I will leave it for the first demo. You will see it a little bit later. And the format is independent, so you can encrypt whatever you want. You put anything inside the Crypt4GH envelope. The byte position preserving is because we have those chunks. So if you want to select, say, for example, byte 100 to 200 inside the file, it's a very simple arithmetic to actually go and detect it in which segment it belongs and then decrypt that segment. And then it's compatible with other standards, for example, HTS-GET. So I will leave this part for the second demo. So now there are some implementations already in Python, in Java, in C, in Golang. These are for standalone tools. And it's not that complicated to implement tools because there are some library already implementing it. And then HTSLib itself has a plugin to load the files in Crypt4GH. So when you use some tools, for example, with this plugin, you will be able to read the files as if, well, pick the files encrypted from disk, but then the plugin will decrypt them for you on the fly. And it's also included in a fork of HTS JDK. So there is some documentation online, and there is some supplementary background information if you're interested. So now we've made some tests, and we use the file NA128.7, it's a BAM file, it's a big one. And then we encrypted it, and then we just read the different reads in it. And then you have a minor overhead. So you see the amount of time it took in minutes to read this gigantic file. And then the Crypt4GH one is not really cumbersome. Now, we have done a second test, which we wanted to query 1000 regions for chromosome 20 into that file. And we get also a rather minor overhead, but the overhead is just for the data access. The mainstream downstream usage is not affected. But in comparison, calculating the checksum of these big file takes roughly 5 minutes as well. So now I come to the point where I'll show you how we connected it into the real world. So the distribution system that we have at the EGA is using Crypt4GH in a demo here. And we delivered the files to a project running at BSC. And for that, we assume that the EGA has already a submitter that uploaded the file into some inbox, and then we have ingested the file into the system. So we assume the file is already in our system, and I will show you the distribution part. So the file that we have received was in Crypt4GH. And what we do is that we actually split the header from the payload. We send the header into a database, and we send the payload into what we call the vault. And we make sure that there is no connection between the vault and the database. So if a hacker goes into the database, they will see a bunch of headers. If they decrypt the headers, they don't have their hands on the payload anyway. And if they go into the vault and they get the payload, they don't have the yellow keys. So we think it is a nice way to do that. And now comes the requester. The requester is a researcher that would like to access the data. Of course, they know how to implement command line tools, but we can make it even easier for them, where there is a graphical user interface. The FileZilla, for example, is doing the job. And then they have on their left the local computer, and on the right, the name of our machine. We call it outbox egarchive.org. And then they make an SFTP connection. So they can connect with their password, they can connect with their SSH key. So it works as well with Aspera. And the idea is that they will just simply drag and drop, and that will do the job. So what the job is to get a file with a header encrypted in one way and re-encrypt the header for that particular user, because this user has this fingerprint, the pink one, okay? So I'm going to show you the idea about how we implemented it, but I'm not going into detail. I've done some other presentations where I show more the details, but in here, I just give you the idea, which is we hardened the security of this outbox. We don't want so we have a locked list of users. We do not allow SSH, we just allow SFTP. It's read-only, so you cannot write files there, you can only read them. We drop privileges. This is quite important, that the system that we are running is not an administrative user that has plenty of administrative rights. What we do is we make the user come and we drop the privileges to the level of that user. And finally, we chroot the user. So we change the environment of the users so that they are actually constrained to their home directory. They cannot get out of their home directory, like one level up, and then they would look at the other home directory of the other users. They would not be able to look at the system files. So there is nothing, there is just their files. So imagine it's a Dropbox where you can just only read. And then there is the fuse file system. The fuse file system is the one that will re-encrypt the header when you do a drag and drop. So when you do ls in the file system, you get the list of files, and this is where you see the constraints, so they cannot get out of the root directory. When they list the data set, they will get the files that belong to that data set, and then when they download the file in Crypt4GH. So here is an example where I run command line mode, where you type SFTP, you pass the private key or the password, and the user I'm using is Jordi Rambla, and the outbox is the machine where I connect. Then I get a greeting message. The passphrase, the key was locked, so I'm requested to input the passphrase for that key. And when I do the SFTP prompt, when I do ls, I get 2 data sets. When I do ls 1 data set, I get the files inside this data set. And you see the file names are EGAFs. They are the IDs of the file. However, there is an option to actually get the real name, and you will see that in the demo. And then when you get a file, you actually will do a download. So this is low-level command line. And you see here that Jordi has access to 2 data sets at the moment I recorded, but then we actually gave him more of them. So now you can also do that with the graphical interface. You would log in, you will see the 2 data sets, and then you go into one of the data sets, you see all the files, and when you simply drag and drop, by magic, you get the file, but this is a file with a new header. Now, the way we implemented that, for those that are interested, we have more details, but in here, we have an OpenSSH server. That's where we do the SFTP. That's where we configure it, where the CH root and the SFTP only. We have NSS. This is the module inside Linux that handles the user IDs. And we connected it to a Postgres, which we made read-only so that you cannot add users if we don't change the database. And then PAM is the one that starts the fuse and also drops the privileges. So all that is automatic, so there is no maintenance. But the database contains the list of users, the list of data sets, the permission for each user to each data set, the list of files, and of course the headers. So now it contains only the headers, so an encrypted version of the yellow key for us. And remember that the vault contains the payload. When a user does a get, what happens is that we actually re-encrypt the header. We send the new header for that user, and the prerequisite, of course, is that we have the public key of this user so that we can make it green. And then we send the payload as fast as possible. So the idea is that the header is the only part that we re-encrypt. And I can tell you that the header is 124 bytes. It's not very big, and there is no overhead in re-encrypting the header. And when we send the payload, we don't touch a single byte or bit of it. We just stream as fast as possible from disk into the Ethernet card and into the wire. So this is where we make it very performant, because there is no business of decryption and re-encryption of the big portion of the file. So the protocol we have chosen to contact the database is Postgres. It's a database protocol. It would make it way slower to use a REST endpoint with HTTP, but we use a binary protocol to contact, and it's compact, it's performant, and also the database will cache many of our requests. So if we make twice the same request, the data is already prepared. And we got one benefit for free that we did not actually think of, is that when you send the file like this, you get kernel caching, which means that the next time you ask for the file, actually it doesn't go into this whole business. The kernel remembers the file and will send it. So this is the system in a nutshell. And we think that this is a performant and secure distribution system. So we have made it into a box. On the right side, you see the EGA archive. So outbox egarchive.org, where the system is running. And then the user on their own machine, they can make a connection into the outbox using SFTP. They will see the files in their home directory, and they can download them. So what they will get is the files are encrypted with some headers, and then we send the same payload, but we re-encrypt the header for that user. Now we do a little bit better. We make it easier for the user. We actually make the connection transparent. So they don't have to make this connection. The connection is made for them, such that when they look at the pink files, they are actually looking at the remote files. And they can do ls and go into a directory and get the files. They will get the encrypted files, but encrypted files for them. And we do even better than that. We actually implement another Crypt4GH fuse that will decrypt the files on the fly for them, so that they will look at the files as if they were decrypted. Notice that the files were never decrypted on disk. There is no trace anywhere, whether it's in transit or at rest on disk, where the file is decrypted. So that way, the file looks decrypted. It's not, but it looks decrypted, and then you can use regular bio tools for that. And these two setups are made by you, the user, one time only, using your private key. This is where you, this is the advantage of Fuse. This is a file system, but you start it in user lands. That means you, the user, can do that. You don't need administrative rights to do it. So we have implemented that, and we think it makes it transparent for the user. So they actually downloaded encrypted files, they use encrypted files, but they never saw that they were encrypted. And by the way, they don't even know it's Crypt4GH. So on the right side, we have a lightweight, fast system with hardened security. We have a secure transport. And then on disk, we have encrypted files for the user, and the system for the user looks live. So if we give the user one more permission to look at one more file, then they will automatically see it in their own home. This is where I run a demo. So I will demonstrate the first part, where I'm going to open FileZilla. I'm going to connect it to the outbox using the user Jordi. So the host is egarchive.org. The user is Jordi Rambla, and then I pass the key for Jordi. So it should normally ask me for the passphrase, but because I did it already, it remembers. Now I'm actually connected to the machine, and I get the listing. As you can see, Jordi has way more data sets he has access to. The owner of the data set is Jordi. In our system, it's not, but we present it as the Jordi. And you see the read-only permission for that file. So Jordi cannot modify this file. Now, let's say that we download the file. It ends up on the desktop because we chose this location. And what we are going to do after the download is the file now is encrypted in Crypt4GH for Jordi. And we will decrypt the file using Jordi's private key. So there is a utility in, this one is written in Python, but you have in other languages as well. So we do go to the directory and we use Crypt4GH. We decrypt, we pass the secret key of Jordi, which is located in this place. And the secret key could be a Crypt4GH key, but it could be an SSH key. So we decrypt the file, and as the input, and the output will be named the same way, but without the extension. And it asks for the passphrase of Jordi, and notice how fast it was to decrypt the file. And now we can look at the file. It is compressed, so I'm going to look at the file using the cat. And I will look at 10 lines, the 10 first lines of the file, or the 20 first lines of the file, or even better, I will look at the lines of the file little at a time, as much as I need, and then I just scroll down to get more. And you can see chromosome 1 with the positions, and there is more and more. So this is the first demo, and notice that I'm trying now to unzip the file, and notice the time it takes to actually just unzip the file. So compare the unzip, the checksumming compared to the decryption. I don't believe the decryption is the bottleneck in here. So finally, the file was decrypted, and now you can actually read the file. So the file is, uncompressed. And now I'm trying to load the file using a text editor, and notice that the file is 2.8 gigabytes. And the editor is trying to load and load and load, and it will take forever to load because it's trying to read the whole file into memory and then display it. And I will spare you the time because it doesn't even finish. The point is that it reaches some point there and boom, you get an error, which is there is not enough memory to do the whole thing. So it even crashed at some times. So now we do another way. Made easy so that the user will not see. On the terminal, I'm going to start the SSH file system. This is the one that will make a connection for us, an SFTP connection to the system, and it will, after that, so first I show you the command, sshfs, the user is Jody 1001, and I connect to the EGA outbox, and I will put the files into this directory. First of all, I create the directory. So make dir, and now I have the directory, and I put it on the desktop. So you should see it at the top there. And I'm going to start the SSHFS that will make an SFTP connection, and I keep it in the foreground so that you can see what's happening. So you can see that it made a welcome to, it got the greetings, and the passphrase, I already saved it. So now you see that it makes some read directory, closing it, and when we go in it, now you see all those data sets, and you can see that it constantly communicates with the server. It's as if you were working remotely, and now it shows you the file. In this version, I show you the original name of the file, not the stable IDs, as we call them. So I open another window, and those files are encrypted. So when I go into the dataset 52, now I have the files owned by Jody in read-only mode, and those I can decrypt them. They are encrypted. I can decrypt them, and I will pass the output. So the private key of Jody is there. It will ask me for the passphrase, and the input will be the VCF files, HG something, loop, and it is, I'm going to send the output to Zcat so that I can uncompress the file, and then I will read the line by line the file. And you can see that we didn't decrypt the whole file. We decrypted, you can't see it, but I'm telling you in the implementation, we didn't decrypt the whole file. But you can see that we downloaded some chunks. We didn't download the whole thing. We downloaded a little bit at a time, and then we decrypt a little bit at a time. So now you can see the file. And at the moment where I scroll more and more and more, I don't know how many lines I need, such that it will go and look at the bottom part. It will go and fetch another chunk that was missing. It was not there yet. It will fetch another chunk, and then the Crypt4GH command will decrypt that new chunk, pass it to Zcat, and then look at the file. There you go. We downloaded about 8 times 32 kilobytes. And then we will do it one more time, but that's about it. So it looks like we are working remotely. Now we can do better. Instead of typing the Crypt4GH command, how about we type another file system that will decrypt the file for us. So on the right side, I still keep the SSHFS running. And now I start Crypt4GH. Now I'm going to show you the command. It's Crypt4GH. I pass a bunch of options, but I will put the files into this directory named EGA files, not EGA Crypt4GH files. So I make the directory on the desktop, and you can see it at the top. If I open the directory, it's obviously empty for the moment because I didn't start it. Now, when I start the Crypt4GH, it asks me for the passphrase of the key. And there are ways to remember the passphrase. You could see on the right side that it downloaded something or asked for the list of files, and on the left side as well. And now inside EGA files, you get some, the same names, by the way, and you get those files, and they look like they are decrypted. The point is that they will be decrypted on the fly. So now I don't need to pass the Crypt4GH command. I can just simply go inside the file, the EGA dataset 52, and I can use Zcat directly because the file is decrypted. The name of the file was, I'm going to use this VCF file. And, and then I look it with less, and then you can see that I get the beginning of the file. We have downloaded some chunks, we have decrypted some chunks, and finally we get the line by line more and more things, and we show you more lines, and we will see normally that we will download more chunks and decrypt more chunks. Okay, so this was one step of the demo. Now let's use a tool. We use the integrative genomic viewer, and we will use a bio tool. So on the bottom right, I have the SSHFS. On the bottom left, I have the Crypt4GH. And the idea would be to start the tool in the middle. Here, I'm using the Linux version 2.8.9. So I start the, you have seen it already, the SSHFS, nothing fancy there, and the Crypt4GH. So you have the encrypted file in this directory. Okay, and you can see the name of the file is .c4gh. All right, and in the Crypt4gh one, I stripped the extension because they are not encrypted anymore. It would be confusing, but it's also needed by the tools to not have the extension. So if you go in the directory, you will see the files, but without the extension, without the C4G8 at the end. Okay, nothing has been dropped on disk. So if you stop those programs, the files are still encrypted on disk. Now I'm starting the IGV browser, and it will first download the reference genome. And we are going to load a BAM file. And because the index is in the same directory, it will be able to use it. I want you to see at the bottom right that we are downloading the file, and at but chunk by chunk. At the bottom left, we are actually opening and reading the file, but decrypting as well. We go to chromosome 20, and there is a position that I made some tests already, and the position is these 534,563, and you could see that the IGV browser will display something, but it has downloading the chunk that is around that position. If you click on it, you get information. So the file was nicely decrypted. You get the read name and multiple information. And in here, you get that you have a T and some C's, but now let's zoom out and see that we are going to need to download more chunks. We did not load the whole file yet. We go chunk by chunk. And there is no way anyway to load the whole file. Nobody has a machine with that much memory. So now you can see that we are decrypting more files, more chunks. And let's zoom way less. And now we need more chunks. You see at the bottom right that we are communicating with the server, and the bottom left, we are reading with some offset, and this means reading some chunks and decrypting them. So I click in different parts, and you see this is quite snappy because we are never dealing with the whole file at the same time. We're dealing with chunks, but all those chunks are nicely encrypted. So this is basically the demos that I had. And now I close my microphone, and Alexander, you can present how you run an analysis pipeline using Crypt4GH.
Okay, thank you very much. So that was very interesting, and it shows one of the advantages of Crypt4GH in that you have random access into an encrypted file. You can read bits and pieces without having to decrypt the entire thing. What I was interested in, if I have a workflow that runs as a CWL pipeline, if I want to run that in some of the other GA4GH standards, such as the cloud infrastructure, how would I go about doing that? So I was specifically looking at the interaction between the standards here and in how to take an existing workflow and enable it to run with a Crypt4GH encrypted file. So the cloud infrastructure has developed a set of API standards for workflow execution, for task execution, and then also for the data and tool repositories. So I was trying to take an existing workflow and then try to make it work with a Crypt4GH source data and just see how that works. If you go to the next slide. The workflow I chose is taken from the Elixir Cloud and AAI GitHub repository. It's one of the demo workflows for the cloud workstream. In this case, it's a CWL-based pipeline, but it's not limited to CWL, what I'm looking at. It's just the mechanisms of running a pipeline. I can run this pipeline locally. There's a CWL tool that can do it, or I can submit it to a workflow service. I can submit it directly to a test compatible service. And I chose this pipeline also because it is interesting in that it uses a lot of the common tools that we look at. So for example, we're starting out here with a FASTQ file. There's FASTQ processing in there. There is BWA mem for index creation. There is Picard, there's GATK. So a lot of the tools that commonly are used in processing are there. How do they interact with Crypt4GH? And then as a little bonus, this pipeline actually already contains a step to encrypt the output in Crypt4GH so that it can be uploaded to EGA. The terminology that is used here is still local EGA. That is really a term that doesn't exist anymore, but it is one of the submission formats for submitting outputs to the archive. So if you go to the next slide, I have forked this demo workflow, and all the modifications I made to run it will be available in here. So first of all, I took the pipeline as is and tried to run it just as a sanity check. And that can be done with CWL tool that locally executes. It locally downloads all the Docker images that are necessary for the workflow. It processes the data locally and produces a result. So that's fine so far. The next step then is, well, what if the source data I have is not a plain FASTQ file, but a FASTQ file or several FASTQ files actually that are encrypted in Crypt4GH? So technically, the only thing I really need to do is to add a step to this pipeline to decrypt the files first, and then the rest of the pipeline works exactly as before because it doesn't know that the source was different. And that was my first approach here. So I encrypted. This particular pipeline takes a lot of FASTQ files as input, but only 2 of them are potentially sensitive. So I encrypt 2 of those input files, the 2 FASTQ input files. And then I wrote a little CWL step that replaces the curl command that downloads the original files with a curl command followed by a Crypt4GH call to actually decrypt them. Then the output of that step is passed on as in place of the output of the original one. So that's a good start. From that point on, the source data is encrypted. That means any file you have sitting on your disk is encrypted, and you don't have to manually decrypt it before you run analysis. The pipeline takes care of it for itself. The pipeline is also geared towards getting the source data remotely, so it can be an HTTP or an FTP server. So if you imagine running analysis on EGA data with what Fred has just demonstrated, you can simply link your input to the SSH or SFTP server on EGA, and then the analysis pipeline directly gets the file from there. You don't even have to download it anymore, and then it decrypts it. Once the data is secure, it doesn't necessarily have to be now in a secure archive like the EGA. So if you have your local data, it's encrypted with your own private, with your own key, let's say. You can now also host this data in the cloud with more security, so nobody but you can access it. So why not put it in an S3 bucket or in a file server? And you can then also link the location of that file to a DRS, a data repository server file. This is a component of the cloud workstream that is not really integrated well with the toolchain yet. But the idea is that you no longer have to refer to a file by its path. You simply say, I want DRS ID 5 and compute on that. So I have I didn't do that in this case, but I have written code in other pipelines that does that. But I'm waiting really for the cloud workstream to integrate that fully with the tools. The same can be done for the code. There is DocStore out there, which is already TRS compliant. And I will probably see if I can upload all the code into a DocStore. So it's public code as it is. If that is the case, then you don't even have to download the code anymore. You can simply say CWL tool, this is my TRS ID for the workflow, and it picks it up automatically from there. most interesting bit to me was what happens to the actual computational bit. So the computation happens on task execution service nodes eventually. So how do I get those nodes to work with encrypted data? If I run it on my local machine, that's really no issue. I have my private key locally available. What happens if I put it in a remote service? They don't have my private key. How do I provide that? And that's the next step you'll see here. So the key handling in test nodes or in remote compute environments is not really something that is solved yet. So that is something that we're looking at for 2021. But at the end of all of that, what we really want to achieve with Crypt4GH as a file format standard is to enable it to be integrated into the tools themselves. So rather than decrypting a file and then handing it off to GATK, I want GATK to natively read the encrypted file. It's very similar if you want to think of it as you can open a VCF file or you can open a VCF.gz file. It understands both formats because they are standard. And what we want to achieve with Crypt4GH is that it can also take a VCF.gz.crypt4gh and know what to do with it without you having to worry about it in any way. That is the end goal. So the code I developed illustrates these steps, and I want to make these the code available so that you can run that on your own, so that you can experiment using source encrypted Crypt4GH data and actually running your own pipelines on it. I'm not quite there yet. I wanted to show a demo, but this pipeline takes about 3 hours to complete on my laptop, so I simply ran out of time recording anything to do that. But I have it working. There's still development that's necessary before the code is shareable, but it will be in my GitHub repository, and then you can run the same pipeline and the same demos on your own if you're interested. So if you go to the next slide. And this is just my last slide. I wanted to show in basic steps what I did. So the first line, CWL tool workflow.cwl workflow.yaml, that simply tells the CWL tool, here's my workflow file, and here are my input parameters in a YAML file. After I encrypted the source files, I changed the workflow by adding my modified first access step to this. So it's now workflow.crypt4gh.cwl. And the only thing that really changed in the parameters is the name of the source files. They're no longer just .fastq or .fastq.gz, but they're .fastq.gz.enc for encrypted files. And then they're decrypted on the fly. And the rest of the workflow works exactly like before. The next step then is to use cloud workstream APIs. So I wanted to submit it into a remote compute node. So I don't have a remote compute node, but at my current company, we have written a set of implementations of these APIs. So I can very easily create a local test node, but there are so many available. So that shouldn't really make a difference. And then I can use CWL test, which has the remote storage URL for remote data upload. And I can simulate the workings of a remote node. At the bottom then, I show one of the things that is still outstanding at the moment. This is the key handling. So on the right-hand side, the fastq in, this is the original source code. I simply have a curl config file that tells me where to get my source files. On the left-hand side is my modified version. And you can see here I'm accessing Crypt4GH encrypted files. And because I'm submitting it to a remote node, I also need to pass the private key and the key to decrypt the private key into that node, which is a bit pointless in terms of security. But that's why we are looking at how to handle security in a cloud very, very strongly at the moment. It is something that will be solved within the cloud infrastructures, for example, with AWS key management systems, etc. But we want to find a solution that makes it possible to take your personally encrypted files into the cloud and work with them there without having to worry about sharing keys, things like that. So that leaves me back to Fred, to the future directions we're looking at.
Yes, but you were actually mentioning some of them already, and the idea would be for the future direction to continue the integration with standard from the Global Alliance, to have more tools to support the format directly. So like you said, if the file format is VCF or VCF, the compressed GZ, it understands both, but now we would like to add to the list that it understands the Crypt4GH format as well. Key management is the elephant in the room. So the file is encrypted, but if you lose the key, then, or if you actually give away the key, you actually have not really secured the file. But this is something that is important, but not really inherent to the Crypt4GH format as well. It's actually valid for any format. I mean, every time you encrypt something, you need to keep the key safe. And then, of course, we need more implementations of it. So imagine now I give you a Crypt4GH file, and then you decide to store the payload into just the payload only into a cloud. So they are encrypted. Technically, you can store it on the moon. You don't have to store it in the same country. So GDPR and HIPAA, they will tell you to stay within the country, but the file is encrypted. You can put it in the middle of the water, it doesn't matter. But what we need to keep very safely are the headers themselves. So this is just one cloud. Imagine in the future, we put all those payloads in different clouds such that we would have a content delivery network so that the file, those payloads are replicated everywhere. And if you are in the US, you would download the file from a cloud that is close to you. And if you are in Europe, you would download from another one. If you do that with the payload, in order to do that, we need to make the lawyers of GDPR and HIPAA, we need to make them understand that the sensitive part of the data is not the payload, it's the key, it's the header. So if you encrypt something with a key and you put it into a box and you lock it, the sensitive data is the key, it's not the box anymore. But if we make them understand that, then we will realize that the sensitive part is the headers, but notice that the header is just about 100 bytes. This is nothing. It's very easy to send to someone. It's very easy to decrypt and send, while the payload would be on a content delivery network, and then you would download it from the closest location to you. So this would be an idea for a future location. And that way, the headers represent a little bit the permission. If you actually have the header for you, encrypted for you, this means that you can decrypt it and get your hand on this yellow key so that you can go and open the file. And that said, now, if you want to get involved, you can contact Rishi at the following email. And if you want to know about the specifications, so the cryptographic choices we made inside Crypt4GH, then you have a full PDF document that describes it. And then we give you some links to the HDS Lead plugin that is already in use, the Python implementations for the Crypt4GH itself, and also for the file system. And this was the presentation using Crypt4GH in the real world, using the why, what, how. We presented why we do it, what we have done, and how we connected it to the real world. And we showed you some demos of encrypted files running. And we showed you the analysis. And it's not a problem, Alexander, that the analysis was not recorded, because we encourage people to actually go and download the code and test it by themselves and realize that it's not complicated. It's just one or two tiny steps that you have to change in your pipeline, and then you get the whole pipeline to run over encrypted files. So it's a good thing. Well, that said, do you have any questions? I see some of them in the chat, and I don't know if I can. In the chat, they say, can you explain more how Fuse is able to provide a decrypted view of the file to the user, but without actually decrypting them? Well, it's going to read a chunk of the file and locate that chunk into one of the segments. Then we decrypt the segments, but we don't drop that segment anywhere on disk. It stays in memory, and we have one segment. Then we output the content of these segments. You might need to chop a little bit the beginning or the end of the segment, depending on how much data you want. And if you wanted more, then we first output the first segment, and then we go and fetch another segment, and then we decrypt that segment. That way, whatever you decrypt stays in the memory of your running process. And if somebody goes into your machine and is able to listen to your process, you're in much bigger trouble anyway. So the second one is from Robert. When using SSH, do the files stay on the remote server or does it cache it locally on your machine? So this is a very good question, and I'm not advertising that SSH, but when we used SSH, we noticed that it downloaded a chunk of the file and did not leave a trace. And I'm sure that there is an option or a way to actually make it stay, but even if it stays, it will stay encrypted. Many tools create temporary files or permanent output files. Are there some recommended hints to indicate their output should be encrypted too? Hard to do in the file itself. Well, I showed you a Crypt4GH file system that decrypts on the fly the files, but there is also the reverse. You could actually give a regular file and make this Crypt4GH encrypted. If you do that, then you have a read and write, but it's on your own machine, such that you look at the files and whatever is on disk is encrypted, but whatever you look at looks like the regular files as if they were not at all encrypted. There is a way to do that if you want. I implemented it, but I did not show it in the demo. And does the system get more secure using secured hardware like SGX chips? And yes, the problem, so SGS is an extension, it's an enclave where you can actually put your some data, and then no other process than you will be able to read this part of the memory. This is some hardware security. The issue would be that in there, well, there's not an issue. You could put in there the key, the decrypted key unlocked, and that way your process running in the enclave, nobody will be able to get their hands on your key, your passphrase, your decrypted chunks, or anything. That way, yes, that would be better. Of course, we exclude the case where somebody would go into your processor and rip it off and look at it, because then there is nothing secure. Are there any more questions? I'm reading the chat, but maybe people would like to voice up and say. No? All right. In that case, this was Crypt4GH in the real world. And on behalf of Alexander and Robert and myself, we say thank you.